Alright, hello there. This is another lecture for Integrated Math 3. We're going to be talking about polynomial long division and how we can use that to find factors, and we'll also be introducing the remainder theorem for polynomials. Alright, so I'm going to start off. We've been talking about polynomial long division, how we do that, and you should have watched a video on Khan Academy about how you can use that to find the factors, which would allow us to write a polynomial in factored form when it's originally given to us in standard form. So I'm going to explain how to do that. Again, kind of briefly. It should be a review if you watched that other video, but I'm going to do it in the context of this problem here. Wait, make sure you guys can actually see that problem. Okay, there we go. So this is a problem that just came up on Khan Academy. It's just a random problem. So polynomial is given to us. P of x equals 2x cubed plus 17x squared plus 41x plus 30 has a known factor of x plus 5. And we want to rewrite this as a product of linear factors. So basically we want to write it in factored form. In order to do that, we're going to need to find all the factors, not just x plus 5. So the key thing is that knowing that x plus 5 is a factor gives us a good starting point, because we can use polynomial long division to find what's left over after we take that x plus 5 out. Okay, so I'm going to go ahead and copy this onto my whiteboard. So let's see. Oops, I hit a wrong button. Apologize. Okay. So let's write down this polynomial. P of x equals 2x cubed Alright, let's go back to my other window. 2x cubed plus 17x squared plus 41x plus 17x squared plus 41x plus 30. And it has a known factor, so it's basically giving us a factor for free, and we have to find the other ones. Alright, so we know x plus 5 is a factor. Okay, so just a bit of review here. If x plus 5 is a factor, that means that we know a 0 would be negative 5. Okay, it also means that if we were to divide our original polynomial, 2x cubed plus 17x squared plus 41x plus 30, if we were to divide this by x plus 5, we don't really know anything about the quotient, the answer that we would get, but we do know one thing, because this is a known factor. If this is a factor, that means we should get a 0 remainder, okay, because it goes into it evenly. So what we're going to do is we're going to go ahead and perform this polynomial long division to get this quotient, because what that'll do is our quotient will be 1 degree less. It'll only be a degree 2, which should be easier to factor. Okay, because looking at this, our original problem here, if I were to just tell you to factor this, I mean, I couldn't do that, right, in my head. I mean, I would have to do exactly this first. I wouldn't be able to just, factor this and take a couple minutes and do it. No, it's not really possible to do. I mean, it would be possible to do if you figured out one factor and then divided it out exactly how I'm going to do it. But it's not possible just from this polynomial to just factor it. Okay, so one of the factoring strategies is once you can find one linear factor, you can use polynomial long division to reduce the degree, and so then you just try to factor what's left. So it makes it 1 degree smaller, it makes the polynomial a little simpler and theoretically easier to factor. Okay, so that's what we're going to do. Alright, so we've been doing polynomial long division for several days now, so I'm going to go through this a little bit quicker than I have been. So remember, look at your leading terms. We want to know x goes into 2x cubed how many times? Well, it's going to be 2x squared. Okay, because x times 2x squared is going to give me 2x cubed. So then we multiply. We use distributive property when we multiply because this is a quantity. So we're going to get 2x cubed. 5 times 2 is 10. That's going to be 10x squared. And we are subtracting here. 2x cubed minus 2x cubed is 0. 17x squared minus 10x squared, that's going to be 7x squared. Now we bring down our next term, the 41x. Okay. So next, x times what is 7x squared? Well, that's going to be a plus 7x. So now we multiply again. 7x times x is 7x squared. 5 times 7x is going to be a plus 35x. And we subtract that. So we're going to get 0 again here. And we have 41x minus 35x. That's going to be 6x plus 30. And then we need to do this one more time. So x times what is 6x? This should be a positive 6. And remember, if we did this process correctly, we know that we should get a remainder of 0. So we do 6 times x, and then 6 times 5 is 30. But we are subtracting that off now, and it's going to be 0. Okay, sorry, I touched the microphone there. So we did get a remainder of 0, but the real important part that we got from doing this is our quotient here. Okay, so remember what we just found out, what we just learned, is we know p of x, here's our original polynomial, right? And we were told, whoops, I don't want it to be red anymore. We were told that x plus 5 is a factor, which means we could also write this as x plus 5 times, let's move over a little bit, times whatever's left over. And so basically, I wanted to find what would be left after I took out that x plus 5. Well, that's exactly what I just did when I divided out this x plus 5. Okay, because remember what dividing is the inverse of multiplication. This is like my answer, and I'm factoring it. I knew one factor was this. I needed to find my other factor. So the way that I do that would be to use division. So we divided by x plus 5, we got a remainder of 0, and this is what's left over. So that means that this is my answer. So this is going to go here. Okay? So in other words, our original polynomial can be rewritten as x plus 5 times 2x squared plus 7x plus 6. Okay? Alright, so this is factored form. However, we need to make sure that it's fully factored, okay? Because we still have a quadratic here. We might be able to factor this some more, and in fact, I'm guessing we can, okay? So, basically, the part we just found, we might be able to factor this even more, okay? But because of the fact that we did this, now notice this is a degree 2. We started with a degree 3. This is a lot simpler than what we started with, because this isn't quite as intimidating. And so this is going to factor to, basically if you remember how this works, you do a times c, you're going to do 2 times 6 is 12. Okay, this is a trinomial. And then your b is 7. So we're looking for two numbers that multiply to 12, but they add up to 7. I think it would be 4 and 3. And so basically the process is remember the x plus 5 is still there. I'm gonna put that aside for a minute. So I'm just looking at the part in the red. So we can rewrite this as 2x squared plus 4x plus 3x plus 6. So basically you find these two numbers and then you split up the 7x into those two, and then you do factor by grouping. And so you look at each group. GCF here is going to be 2x. So what's left is going to be an x plus 2. My GCF of my second group is going to be a 3. So it's going to be an x plus 2. And because we have this x plus 2 in both places, now this is like a common factor. This is our GCF. We have two terms now, but we have a common factor of this x plus 2. So if you factor this out as our GCF, what we have is x plus 2 times 2x plus 3. Okay, and so remember, I still have this x plus 5, and so the fully factored version of this would be x plus 5, which was given to us, and then we just found x plus 2, 2x plus 3. Okay, and so now the only thing left is to go ahead and put that in and make sure I got it correct here. So I need to make sure you can see Khan Academy again. Okay. And notice it says as a product of linear factors. So that's why you need to keep going after you did the polynomial long division, because what was left was quadratic. But it says it has to be linear. So it's x plus 2 times 2x plus 3. So x plus 2, 2x plus 3. Make sure I'm doing everything good. Okay, so we got it. So this shows you how polynomial long division can be used to help you factor polynomials. Okay, so we spent quite a bit of time talking about graphing, finding zeros, maximums, minimums, increasing, things like that. And then we kind of went aside to polynomial long division, but this is where it relates because it helps you find the factors. And if it helps you find the factors, it's helping you find the zeros of that polynomial. Okay? And so that's really one of the main reasons that we do learn about polynomial long division, is because it can really help you factor something that otherwise is a higher degree and really hard to factor. Okay? Alright. So I hope that helps. From here, what I want to do is I want you kind of transition a little bit, and I'm just going to introduce this today. We'll spend more time working with this next week. So what I need to do now is I need to close off Chrome and go back to my whiteboard. But I want to introduce the remainder theorem. Okay? Or what's called the polynomial remainder theorem. Alright, so I'm not going to worry about proving this today. I just want to kind of tell you what it is and show you how it's useful. Okay, so the polynomial remainder theorem says if I have a polynomial, let's call it p of x, and let's say I divide it by constant, or no, sorry, not a constant a. I divide it by, sorry, I'm trying to keep track of my thoughts here. I divide it by a linear factor x minus a. Okay, so a would be a number. So for example, x minus 3. Okay, now this is key. Notice it has to be by a linear factor. There can't be a coefficient here. It's just x minus a number. That's the only situation the polynomial remainder theorem applies. Okay, so we have a polynomial, and if we divide by x minus a, and I just wanted this as an example, I'm going to erase it so it doesn't confuse you guys for the theorem. But if we divide it by x minus a, we'll say the remainder is k. Alright, so far I haven't really said anything. But what the polynomial remainder theorem says is that if we evaluate p of a, that equals k. Alright, so what this is saying is if you were to divide a polynomial by a linear factor in the form of x minus a number and you get remainder k, the remainder is the same thing as the value of the polynomial evaluated at a. Okay, so I'm going to go through example here. I'm just going to make up a polynomial and show you that this works. Now, I'm not trying to prove it necessarily. I'm just trying to help you understand what this is really saying. So let's create a polynomial. F of x equals, let's do third degree, 3x cubed minus x squared, not too big of numbers, 5 plus 5x minus 3. Okay. All right, and so let's say we want to find I'll word it like this. Let's try to find f of 5. Okay. Now the easiest way to do this would be just to plug in the 5, use your calculator, and we'll do that in a minute to kind of check. But according to the remainder theorem, another way to find this would be to divide this by x minus 5. Now notice the sign change in when I wrote this in the remainder theorem. It's always x minus a. Okay, so f of positive 5, this is positive 5, but we're dividing by x minus 5. So one way to think about that is that the number is the same that would make this equal to 0. Because positive 5 minus 5 would make this 0, right? So what we're going to do is we're going to divide our polynomial by this x minus 5. And one thing about the remainder theorem is when you're doing it just to find the remainder, you don't necessarily really care about the answer up here. I'm still going to do it just so you keep good habits, but notice that we're really only, in this case, we're really only after the remainder. Okay, so x times what is 3x cubed? Well, this is going to be 3x squared. So multiply x times 3x squared is going to be 3x cubed. Negative 5 times 3x squared, that's going to be negative 15x squared. Kind of jumbling my numbers up here. So remember, we subtract, which means we change our sign, so that becomes a plus 15. So that's a 0. This is like a negative 1. So negative 1 plus 15, that should be positive 14x squared plus 5x. Next, x times what is 14x squared? Should be a plus 14x. So 14x squared. And then we have negative 5 times 14. So that's going to be, I believe, negative 70x. And we are subtracting it, remember? So this is going to actually change this to a plus 70x. So 5x plus 70x is 75x. Of course, 14 minus 14 is going to be 0 here. And we bring down our minus 3. Our last one, x times positive 75, is going to be 75x. So we do 75 times x, and then 75 times negative 5. Let me think. 10 times 75 would be 750, so it would be half of that. So it would be, what, 375, I'm pretty sure. 375 times 2 should be 750, so I believe that's correct. I guess I'll find out in a minute. Hopefully I didn't do my math wrong. Okay, so now we need to subtract, which means we're going to change our signs. So this is going to be 0x, and we have 375 minus 3, so this is going to be 372. Okay, so if I did my math correct, what that means is that f of 5 should be equal to 372. So now another way we can do this is the easier way, really. This was harder, this was longer. I would never suggest you do this to answer this question. If you're trying to find the easiest way, don't do it like this. I'm showing you to demonstrate the remainder theorem. So now let's do it the easy way. So let's just plug 5 in. So we have 3 times 5 to the third minus 5 squared plus 5 times 5 minus 3. So let's see, 5 to the third. 5 times 5 is 25. Times 5 again, that'd be 125. So this is going to be 3 times 125 minus 25 plus 25 minus 3. So these are actually going to cancel out. So we have 3 times 125, so that should be 375 minus 3. So that's going to be 372. So notice that we got the same thing. Okay? So that's not a proof that the remainder theorem works, but hopefully it at least demonstrates that, it's very unlikely we would end up with the same number if this wasn't a in fact a relationship. Okay, but so I'm just introducing this today, and this is really useful for a lot of things. For just to connect it to a little bit what we just talked about finding factors. So remember that if x minus a happened to be a factor, okay, which if you're trying to graph a polynomial, you're probably trying to find the factors or trying to find the zeros, really. And so basically what you're looking for is to figure out, okay, is this a zero, is this a factor? And so instead of having to do the whole process of, whoops, I moved something. I think I moved it from there. Rather than having to do the entire process of polynomial long division, which is admittedly kind of long, and by the way, there is a shortcut way, which I may or may not get to, but it is kind of long, just to figure out if you get a zero remainder or not. Instead, you can just evaluate it. So if I wanted to define, okay, is x minus a 5 a factor of this, I can just plug in 5 here, and if the answer isn't 0, that means it's not a factor. All right. So in a nutshell, that's kind of one of the main uses of the remainder theorem, is that it's really a much faster way to check if a linear factor is going to in fact be a factor of the polynomial, or if not. All right. So that's the end of this lecture, and have a great day.